Okay, so yeah, I am Alison Monaghan. I'm the head of geothermal at BGS, and previously I was science lead for the UK Geoenergy Observatory in Glasgow. So what I'm talking about today are experiments we actually did in 2023 and 2024 as part of the GEMS project. We've heard several mentions of the GEMS toolbox, and this was a part of the project looking at actual on-the-ground experimentation. And what we were planning to do in these experiments is look a bit at when we put heat into the ground, how far do thermal plumes go, in how much time, and how do they spread out under the ground? And why is it important? Well, for heat abstraction, we need to know how far apart to put our boreholes. And for mine water thermal energy storage, we want to start to understand the processes that are happening in the mine working and in the rock mass above and below the mine working that Milen just talked about and others have talked about, how the heat goes into those rocks. And then also, obviously, you want to know how the heat comes out of those rocks when you're doing the mine water thermal energy storage, as well as in the water within the mine workings. We've already, back in 2021, after we drilled the boreholes in the UK Geoenergy Observatory in Glasgow, kind of characterised some aspects of the character of the mine working. That's the images that are up here, some of those, open voids, collapsed GOF and so on. But what we did in this work was look much more broadly at the mine workings. And we did a series of experiments using this kind of at-scale infrastructure we've got at Glasgow to actually measure some of those heat and flow changes under the ground. So we did 2 experiments, and I'll explain a little bit about what we did. So using my pointer, the first experiment, we pumped mine water out of the Glasgow upper mine working, which is about 50 meters below the ground. So we pumped it up out of an abstraction borehole. We took it in and we used the heat center to raise the temperature of that water by about 5 degrees centigrade, and then pumped it down an injection borehole in the same mine working. These boreholes are only screened at the mine working interval, and we've got lots and lots of sensors both across the mine water pipe system, at the wellhead, down the boreholes, and we've also got fibre optic cables that are installed down the edge of the casing all the way down the boreholes that give us that temperature profile down the outside of the boreholes. So we've basically can measure temperature throughout the mine water system and in the rock mass surrounding it. So in this first experiment, we did this heat injection. We added heat to the system for about 17 days. We knew from previous pumping tests the transmissivity of this particular mine working is around 1,000 meters squared a day. We used a flow rate of 12 liters a second and a temperature difference of about 5 degrees that we added on to the mine water. And these boreholes are spaced about 135 meters apart. And in this first experiment, we started to see thermal breakthrough at the abstraction borehole over here in about 5 days. And we classed that thermal breakthrough as a rise of 0.1 of a degree centigrade. Then contrasting that, in the second experiment, what we did was you used a different 2 boreholes that went down to a deeper mine working, the Glasgow main mine working, at about 85 meters down. The transmissivity of that mine working is about double that. It's about 2,000 meters squared a day. We used the same flow rate and a similar temperature differential, about 4 degrees centigrade. And those boreholes are a similar kind of spacing apart to the first experiment. That experiment we ran for about 5 days, and in that experiment, we started to see that thermal breakthrough just over 2 days into the experiment. So basically, we did a very similar experiment, similar flow rates on 2 different mine workings, and they gave quite different results as to when we saw the thermal breakthroughs in those mine workings. So I'm going to spend a bit of time now describing what the mine workings are like, and then we'll come back to why we think we see that difference. Okay, So just looking at the mine plans and what we found when we drilled the boreholes, first of all, these two images on the left-hand side are that higher coal seam at about 50 meters. There's a mine plan from 1884 and then one from 1933. And our boreholes here, we've got our reinjection borehole up here and our abstraction borehole down here. And maybe what you can see on this earlier mine plan is that there's stoop and room or pillar and stall mine workings. And then there's a bit in the middle where we had short wall essentially workings that were older. And then these were totally extracted. And what we see is the kind of grain of the mine workings is in this kind of direction. And so the flow during the pumping test or the heat injection test is kind of across that flow. So that's something to kind of keep in mind. And the different mine working types that we saw in those boreholes, we saw pillars and voids. We saw loosely packed stowage or waste within the mine working. And we also, in another site over here, we drilled through a pillar, for example, so we saw intact coal. So different range of things within the mine working. And then the deeper mine working, this mine plan over here, what we see on this mine plan are dotted roadways, former roadways that have actually been extracted by the time the 1933 plan was drawn. And we used these two boreholes for the Glasgow main experiment. This is the abstraction borehole down here and the reinjection borehole up here. And when we drilled into those boreholes, this is a downhole image log from the abstraction borehole. You can see there the black space, that's water-filled void, and there's kind of a floor lift zone as well. And the other borehole, it actually went into a roadway, which then had kind of collapsed material at the bottom. So this Glasgow main mine working, we interpret as being much more open voids compared to the Glasgow upper mine working that had a greater proportion of pillar and stall workings and sort of stowage or waste material. So that gives us some clue why potentially the thermal breakthrough times are quite different in those mine workings. So one of the things we've done is to look at a range of different data to then take those kind of small diagrams and think more broadly about what the mine workings actually look like, partly so that people who are doing numerical models can actually really try to understand what these mine workings look like. So this image here that I've drawn is the site that was kind of like a monitoring site. It wasn't one with the abstraction and reinjection boreholes for the Glasgow upper. But essentially, the integrating the borehole and the mine plan and the hydrogeology evidence, and also a lot of field work that some of us did many years ago, and the knowledge of, we used to have an ex-mining surveyor worked with us who passed on a lot of knowledge. So we've used all those to kind of draw these diagrams of what the mine workings might look like now. And you can see the inspirations, for example, for this diagram. This is an old open cast site where we can see pillars of coal. We can see the stalls or the rooms, and you can see collapsed materials in there, but you can also see the voids. And that's the kind of thing we see when we drill into these workings. And then a similar kind of diagram. This is between our reinjection borehole and our abstraction borehole over here. So we interpret quite different types of mine working. We see a lot of evidence of packing the mine workings and stowage in this area, similar to what we see on some of these field analog photographs. This is a photograph of me in 2003, going out to open cast sites, looking and logging those sites and understanding what these rocks look like on the ground. Here you can see a coal seam, kind of collapsed waste and kind of more finer waste underneath. And again, so these images show that between these boreholes, we've got quite complicated fill within the mine working. And so that's why potentially the transmissivity is lower. So now I'm just going to go back to the experimental results. So I will explain these graphs. So these are two experiments. This is the first longer experiment. So on these graphs, we've got temperature on this y-axis, and you can see between the blue and the purple lines on this graph, this is about the 5 degrees centigrade that was applied. So the heat injection pulse. And then the red line is the difference in the temperature between the abstraction and the reinjection boreholes. That's the scale on the right-hand side for that. And so what we see when we start pumping, that we see the thermal plume initially, it's fairly flat, and then we start to see this thermal plume coming through in our abstraction borehole on a timescale where we see that after about 5 days. And then on the other mine working, the same is true of this graph. This is the temperature differential that we've applied, the heat injection pulse. And in this other mine working where we've got more open voids, the timescale here is just 5 days. So we see an initial sort of flat patch, and then we see the temperature start to rise. So we start to see that thermal plume coming through. And this is measured at the sensors at the wellhead, right in the flowing mine water in that open loop system. I'm going to show you a really complicated graph now, but I'm just going to point out a couple of things on this graph. So what we can see here, the different colors represent sensors within the system at different places. So that's, we've got a lot of sensors, so it's complicated, but essentially you can see the same thing I showed you on the previous graph, which is the differential between what's going in the injection borehole and what we're abstracting. That's the sort of 5 degrees centigrade temperature change we're putting in. But if we look at what's going in, that is relatively flat, apart from some things with the system. But if we look at down here, I want to first look at this darker purple line. So this is the temperature at the mine working using the fiber optic cable, this darker purple line. And what it's doing is it's measuring through time the temperature change as the thermal plume comes through that borehole. So initially, a bit like the other graph, we saw it was flat. And then very gradually, that temperature starts to rise as we keep on pumping more and more heat into the system. I'm not going to talk about the recovery part, which is when the pumps were turned off. And then I just want to draw your eye to this very wiggly purple, lighter purple line behind it. This is a borehole which is 10 meters away from where we're injecting the heat. So it's closer than that other borehole that I just showed you that was 135 meters away, which is the darker purple. And what we can see in the borehole that's closer away, if you can ignore all the daily spikes, which is due to the way the fiber optic cable was installed, we see a smaller patch of a flat temperature and then a more rapid rise in temperature. And so the borehole that's closer, the warm water gets to it first, as you would expect, and then the temperature rises more rapidly. The borehole that's further away, the heat takes longer to get to it, and when it does get to it, the temperature is rising more slowly. When we went to the second experiment, I've got a similar graph that I'll not go through in as much detail. We essentially see this is the abstraction borehole down here. So this is the thermal plume coming through. But what's important here is that the rate of change within that abstraction borehole is about, well, the previous one was 0.3 degrees centigrade per day. The rate of change on this one was 0.14 degrees centigrade per day. So you can see that those different types of mine working have got quite a different rate of change of the temperature. This is a summary slide that basically just says what I've just said, so I'm going to skip that one, and I'll go on to the final slide, which is a kind of synthesis of some of that. So I guess what we're trying to do in this experiment and presentation is look at some of the different processes of how heat moves and flows within the mine working and how it moves into the rock as well as in the water. And we can see potentially the difference between heat flowing in open voids, where like flowing through conduits and used by advection, and those flowing through backfilled waste and other material types where we see conduction dominated systems. And potentially what we're seeing This is a plan view of what we're seeing, but what might be happening, we think, is that some of that heat in those mine workings with all the stowage, the heat is actually starting to go into those kind of bits of rock within there. It's distributed and dispersed within that, and also into the fractures above and below. And we can see that by using the closer borehole and the further away borehole, the way the thermal plume sort of spreads out. So in summary, having a site where we can do these experiments and really measure it starts to tell us about the real thermal processes that are going on underground. We can see changes happening in days. And we think we can start to see how the plume is spreading out, potentially how some of the heat is going into the different types of mine working. And that's important. It's important for mine water thermal energy storage to know, how much heat is going in versus how much heat is kept in the water. And it's important for heat abstraction, because what we've shown is that in a mine working with those kind of levels of transmissivity, you certainly wouldn't be wanting to put two mine water schemes within a few hundred meters of each other, which everybody kind of knows anyway. That's why we do cross-seam schemes, why we put things further apart. But it's starting to give you that actual measured numerical basis, looking at the temperature variations between those boreholes. So I will leave it there. Thank you.